Thank you for showing up. I know it's the last talk, so it's always I'm standing between you and beers or dinner or whatever you do at 5 in this country. Thanks to the organizer. Well, London is a tricky bit. It would be beer o'clock 5. Thanks to the organizers for organizing this and for giving me the opportunity to be here. It's very nice and also very intimidating to talk to you guys. And let me start with a couple of disclaimers. So here you see some words, informational and topological. Really, you should think about this in that term that Mason doesn't want me to use, which is higher order. And by that, I mean polyadic. Okay, so the reason is I'm gonna show you a couple of, basically tools and ideas that we've been playing with over the last year, a couple of years. And they're all based on this idea of going beyond networks, effectively. We're using tools that are beyond networks, okay? And it's gonna be topology really more than information. And then second disclaimer, I promise too much. If you are interested in what we've done on aging, talk to me later, please. I'll try to stay because I want to stay in time, and I know I'm the last one today, so it's better if we just skip that. And also we have like half of the story, so just catch me later, okay? For the beer above mentioned. Okay, so why we're talking about topology? Okay, so the joke among mathematicians, right, is that topology is that branch of math that tells you that if you have a mug and a donut, they have the same topology, okay? Now, the physicists or the biologists typically says, okay, but if I have a donut, I want a donut. If I have a mug, I want a mug. Okay, so why should I care about having both? And then the answer to that is that if your system does have some topological structure, because of this robustness to transformation, stretching, and so on, it is very robust, and it's probably very important, or at least has some meaning in there, okay? So the question is, can we actually look at, techniques to extract topology from our data? There is also another little joke that I like very much when talking to network scientists in this kind of context, which is, the origin story of graph theory. I don't know if people here recognize it, but those are the bridges of Königsberg. And this is actually, so the problem here was that Mr. Euler wanted to go through all the bridges exactly once, okay? And then the question here is that, how do you do that? Well, you don't really care about, the islands, how big they are, about the geography. Because the problem really is just about the fact that you're connecting these different islands here, okay? So what you do when you try to solve this problem is you shrink down these connected components to nodes, okay? So you end up with a graph. So in a sense, you can say the graph theory is just low-dimensional, zero-dimensional topology, okay, to some degree. So there you go. We do graph theory also at the same time. Jokes aside, why topology is important? What kind of additional dictionary does it give? So we're familiar with like the dot, the node, or and the edge, which we're going to call 0 simplex and 1 simplex. And if you start using a topological, at least a very simplicial description, you can also have the triangle. So now the triangle is the actual triangle where you have the full part in there. So it's not just the sum of the edges. Okay. More formally, in general, what you can actually describe are which you use as bricks of the description that I'm going to show you later are k-simplices. Okay, which are just sequences of points. Typically, if you have k-simplex, it's k plus 1 points in there. Okay. If you are in an actual space, there are rules that you need to have, but if this is an abstract simplicial complex, then you actually don't care there about it. So it's just a selection of, for example, variables. If it looks familiar, it makes sense, because, for example, if you have worked on multivariate information theory, you have something that looks like that, this joint distribution of values of a bunch of sources or stochastic variables. Now, all of these things, because of this group interaction, or higher order, in the sense that it's more than pairwise, that's what we call higher order, okay? Intrinsically higher order structure. There is something else, though, that you get when you have a simplicial description, so when you put together a bunch of simplices, which is that guy there, okay? So this is called a simplicial complex. I'm not gonna, by the way, one more disclaimer, I'm not gonna get into any of the details of this because we had the tutorial yesterday, so I'm just gonna show you pictures, wave my hands, and hopefully, topology is gonna be clear to you. So simplicial complexes are basically a bunch of collections of simplices together with one special rule, which is a downward closure. So if you have a triangle, you need to have also all the subfaces in there. So if you have a triangle, you also have 2 edges, and so on. The part that I'd like to point your attention to is this hole, okay? So this is something that I would claim, or at least I would call, intrinsically, let's say, non-local, with a user notation. Because the reason is that to actually have this kind of hole in here, you need coordination among a bunch of edges and so on, okay? So when you actually look at the shape, the homology as it's called, of this superficial complex, you're actually looking at something that we could describe as mesoscale, okay, in terms of the system that you're looking at. So it's not just the local statistics, okay? Now, what is the problem when we do this in the wild, okay, when we actually look at data? Well, if we were to have something that looks like this, which is very pretty and neat, regular, there's not, you can just probably get away with a statistical description, even if you were to change in time. For example, it opens and it closes. Over here, you could probably, I don't know, do something smart with the distribution of path lengths, for example, to pick up when it's open and when it's closed, okay? Unfortunately, reality looks a lot more like this, okay? So now here, you have a large sphere, you have holes, other smaller features, you have a pathetic attempt at putting noise on that, the pink stuff, it's my attempt. So is this like a large sphere? How do we actually measure that? Topologically, this is a sphere at a large scale, and then it has all these other features inside, okay? Note aside, I took this picture from a conspiracy website. It was something about, I don't know, lizard man, homology, and I think that's where their model of the world. So don't read what it's in there, but they have the most amazing pictures. So, if you can scrub your chronology afterward, then it's even better, okay? So going back to actually what we are interested in is that would like to go from a situation like the one before, from data to a simplicial description. And then here there is a problem, right? The problem is, suppose that we are in an easy case where you have points in a metric space, those points there from that pseudo donut or thingy. You want to recover the fact that it's something that looks like a disk or a hole, a disk with a hole. Now, the standard way to do this in a metric space is basically by looking at epsilon balls around these points, or fat points, depending if you want to do like point shaming. And then when they overlap, you put an edge. When you have like 3 of these and they overlap, you put a triangle, and so on and on and on. Of course, this actually just means kicking the can down the line, right? Because then the question becomes, what is the right epsilon? What is the right radius for my point or my neighborhood actually here, okay? What persistent homology does is flipping the problem around. So saying, well, I'm going to do this for all the possible radii in this case, or for a set of values depending on what I do, and then I'm going to collect all my simplicial complexes that I have sort of built at each radius, put them in a line, one after the other. And the line, which is not a line, it's a sequence, it's called a filtration, because you're filtering the thingy, here the simplicial complex. And in this specific case, the filtration also is a chain of inclusion. You see this guy is inside this guy, and so on, okay? Then you look at it, or actually analyzing using pretty complicated algorithmic machinery, and then what you're interested in is in looking at, for example, at the topological features that persist throughout multiple, epsilons in this case, okay? What are topological features? Well, the obvious one is connected components. You start with many, and then they merge together, and then they sort of, at the end, there can only be one. Highlander quote for you there. And then, people are too young here for Highlander. Anyway, they're making a new series now. Then you can actually look at one-dimensional cycles, which are holes bounded by one-dimensional simplices, 3-dimensional holes, and so on and on and on, okay? In this case, since we made the example being metric, if you live for a long time, it means that feature lives for a large number of these epsilons, okay? So it's like an important feature in this sense. These things you see down here are called barcodes because they look like barcodes, and you get one for every dimension. So 0-dimensional holes are non-holes, connected components, 1-dimensional holes, 2-dimensional, 3-dimensional cavities bounded by 2-dimensional holes, and so on. You can go up, okay? Now, something that you can do then is measure distances between spaces, okay? And what I mean by that, well, I mean that there are ways using these barcodes or the persistent diagrams, which I'm going to show you in a second, but we're not going to use them really. There are ways of putting basically distances between these topological summaries, as they're called, okay? And what I mean by that, the idea is that you're able to say that these two guys are more similar to each other than to this other guy over here, okay? Now, papers are there. Don't really care about that today because, after all, we're going to use the persistent homology machining, but we're not going to really use persistent diagrams so much, but they're there. So in the end, the typical pipeline is like, instead of looking you're looking at barcodes, you look at persistent diagrams, which are the same thing effectively. Every bar has a birth and a death. Every point has 2 coordinates, birth and death, and they typically are about the diagonal in this representation because you first are born, then you die, modulo, I don't know, Jesus Christ, whatever. And then the pipeline typically is something you start from data set, you extract a simplified representation, you measure this topology in dimension 0, 1, 2, and so on, and then you have some measurement there. As I said, we're not going to actually do this. I just wanted to make you aware of one way of doing this. Okay, so this is how you would go if you were comparing directly the topological structure, the one. We're not going to do that because we're going to need a little bit more information. Okay, good. What does this tell us about brains? Well, it all started at some point when I was in Imperial, and I was talking to people that were doing a very interesting experiment. So they were recording people in 2 sessions. In one session, they were giving them placebo, water. And in the other session, in resting, they were giving them psilocybin. Now, for the naive among you, psilocybin is the active principle of magic mushrooms. So in one of the 2 sessions, they were high as kites, the subjects, okay? And this is all fMRI, and it's going to be fMRI throughout the whole talk. And their observation was actually rather underwhelming because they were finding very large behavioral changes. But in terms of what they could pick up as changes were just like some very localized, let's say, deactivation of the brain, okay? So what did we do? We came in and we basically cranked our machine. And what do I mean by that? So we built correlation matrices from bold time series, parcellated on standard atlas. In this case I think it was AAL at the time. So about 90 nodes, okay? So you end up with matrices that are 90 by 90, roughly. It's not true, 89. And you can look at this as a weighted, as a completely connected weighted graph, for example. Or for the sake of today's presentation, you can think 1 minus the correlation as a distance and do the game that I told you earlier, okay? That's not exactly how we did it, but it doesn't really matter. That's it, the idea is the same. So we did it, and lo and behold, these are the persistent diagrams at the group level. So we put all the generators together for dimension 1, so one-dimensional cycles, in the placebo and in the psilocybin case, okay? I was beaming, I was super happy because, of course, big difference, easy, Of course, the neuroscientists with us were not so happy because they were like, okay, this is good. We knew there was a difference, but then, where is this different, okay? So what is the interpretation of this topological change between one condition and the other? And so we built something that should make every mathematician in the room scream inside, that we call scaffolds, which are new graphs, okay? We're starting from correlation matrices, functional connectivity, and we're ending up with a new graph at the end too. The way we do it is by basically going back to the filtration, the one that I showed you earlier, and then we track every generator, every one-dimensional cycle in this case. And what we do is that we choose one representative cycle in there, and then with those edges we put them back into an empty graph at the beginning, weighted by the length of the persistence of that generator. Okay, so we're basically encoding information this way. You can actually count how many times the edges is present in one of these cycles or the weighted, it still works. Now, why mathematicians are not happy with this? I'm a physicist, of course, so I don't care. But it's because homological generators are classes, equivalence classes. So you have multiple cycles around the same hole that are valuable. Okay. There are ways of addressing this. At the time, what we did is we checked that the ones we're getting were small enough at the beginning when they appear, and they didn't change too much until the end when they disappear. Okay, so we basically a posteriori checked that it was fine. There are other ways of doing it, in a more controlled way now, but the idea, it wasn't really an issue in our case, okay, because we're basically choosing the tightest or almost tightest. And just to give you an yes.
I just want to get some intuition.
Yeah.
For the data we're dealing with.
Yeah.
So you said that between the two groups,
yeah,
there were some weak effects.
Yeah.
In the average activity.
Yes, there was just a localized activation in the thalamus and so on. I think that was the main thing.
And so, but if you look at the correlation matrices, maybe there was a bigger effect.
Actually, it wasn't. If you looked at that from the network point of view, they were not finding anything very special. That's okay, why we came in.
The correlation matrices, which tell you the fluctuations about the mean,
yes,
also looked similar.
Very similar. And listen, so there were two problems. The first one is, well, the observation was they couldn't really find very interesting differences. There might have been a problem with threshold because, as you see here, I'm not thresholding anything. I'm just taking all the scales, right? So it might have been that the way they were doing it was wrong, but actually we tried also later and we couldn't really find anything that was in any case, in any way as strong as the effect that I'm going to show you in one slide. Okay.
And then, and so, but now you've got this correlation matrix, which you think of as a graph, and I'm trying to think of ways in which you would get things like the graphs that you're showing here.
The way it works, it's what you're finding is that you basically have correlation. Like I am correlated to you,
Chains
you're
of
correlated to
correlation.
someone else, but,
Exactly.
and the other person is correlated to the other person, but I'm not really strongly correlated with that
Right.
person over there.
And so it could be that there's a common latent factor,
Yes,
for instance.
of course, we don't know that.
That's correlating
Yes.
these variables that we're looking at, and so these could be potentially cliques that.
Here you actually find the anti-click, right? You find where the clicks aren't, effectively, because you're looking for the holes, for the topology, for the absences of connectivity.
I see. Yeah, well, that's interesting.
Is the assumption here that this graph is stationary?
Well, in this case, so in this specific case, we just took the whole time series because it wasn't very long. We went one graph per person,
Okay.
per condition. So it was just that. Yeah.
Magic mushrooms, they're probably hallucinating all sort of stuff, and
I'm going to show you later something that where there was no mushrooms, but we did this in time, and then you can see fluctuations, but they're not that many, that strong fluctuations, at least in rest. But yes, of course.
So like in your barcode, you have your 0-dimensional holes,
Yeah.
1-dimensional, 2-dimensional. Here you're showing us like every feature.
One dimension.
So you just ignored the other features?
I'm ignoring the others because the H0, it's honestly a bit boring. And H2, since it's a small system, it's basically almost always empty in these cases, right? Because there are limits of how many you can build with so many nodes, right? So H1 was the one that had the strongest effect. Yeah.
So is it the edges that are weighted or the holes?
The edges in here are weighted with the persistence of the corresponding cycle. Okay. So that little yellow cycle was weighted very little, and then the green one is a lot. Right? So you put it back in here.
So if the edges are around a hole, then
Yes,
they're weighted.
exactly. They're weighted like that. It's really easy. You just cycle, put it in. It's nothing magic. Yes.
What if there's an edge that?
I don't hear. Sorry.
Sorry. What if there's an edge that belongs to two holes?
That belongs to.
Two cycles.
It just you just sum the.
Sum them.
Yes. Yeah. Sorry, I should have said that. I've been doing this for a long time, so I forget elements. Yeah, I'm never gonna finish this talk. Please.
Can you give some intuition for what statistically must be true
Yeah.
for a correlation matrix to have a graph like this? Like what kind of statistical structure are we talking?
So I don't have an answer to that. I have another example that I can give you. So thinking about something like this, we tried building nodes that had, like, for example, two sources inside, and the result of the signal was some sum of them. And then you have another node, which is one of the sources plus another. And then you have another node that has one source plus another. And that kind of thing can generate things of this type, right? So you have sort of mixed effects in there. It's not the only way, I assume, but this is definitely one way. Okay?
And it wouldn't have cross edges.
No.
It would create the
Would have no. I mean, the cross edges are all there because you have all of them, but they're just weaker, right? So they appear later down at some point. You get everything. It's just that. Yeah. Yes.
If I were to summarize this, tell me if I'm wrong. You're sparsifying your graph, trying to preserve topological structure. Is that like a one sentence?
Well, yes. I mean, you could say that way. So I'm basically recompressing the topological information that I have expanded there into something that is a graph, and so I can sort of see where it is with all the caveats that I made earlier, about it. Okay. Can I continue? Yes. Great. Let me show you one. Okay. So this is the thing. And to that point, actually, these scaffolds they're not basically the same thing as just thresholding your graph, right? For example, if you threshold the original matrix from which I computed this guy at the same density, I get something that even by eye looks very different, right? And I can do something else, which is, for example, I can take the edge in here that has the minimal weight in the original graph, threshold at that level, and I end up with something that is completely different again, okay? So what I am doing here is not just some normal version of thresholding, but it's, I think, rezipping this topological information and localizing it somehow. So we did this, and we ended up with something that looked like this. Left, placebo, right, high, well, psilocybin, okay? There is a little bit of cooking here in terms of visualization, but the idea was that the tails are much stronger over here, okay? So actually when this thing came out, since it was, and you can see that, they're much bigger, the effects are even just by eye much larger, okay, much different. So when this came out, since it was about psychedelics, there was quite a bit of noise about it. People said that this was like very, very much more connected. Your brain is more connected when you're on psychedelics, but really that's not well, I mean, people smiling in the rooms probably they tried, so they know. I would say it's actually a distributed reorganization of the hierarchy of these circuits, right? Because that's exactly how we build this thing, by thresholding and looking at them and putting them together, okay? So why am I telling you about this, and why am I telling you, did I say fingerprinting earlier? Because we want to say whether there is a topological individual structure hidden in fMRI in your bold signal, okay? So how did we do this? We took very long time series of resting state. We sliced it in different windows, and for each window we computed a functional connectivity. And then that way we have like a bunch of different graphs, functional connectivity graphs. Computed the precise homology, and then we computed a scaffold for each of these ones, okay? Forget about the intermediate step. We're going to just focus on the functional networks and on the scaffolds. Right? And of course, the first thing you can actually do once you have a sequence of graphs is just looking, for example, how they are basically a recurrence plot, like how they're correlated in time, how similar matrix at time t is to the matrix at time t plus tau, okay, something like that. And already by eye, you see that the scaffolds seem to be more blotchy, right? But for us, the interesting thing was, okay, if I have recording of myself today and a recording of myself in 2 weeks, am I more similar to myself than I am to the other cohort? And so we took 100 subjects, HCP, and we did this. We basically computed all this, and then we measure the distances between the scaffolds. My scaffolds today and my scaffolds in 2 weeks into different sessions, and also the other one. Okay, you can measure all the distance between all the possible things, and even by eye, and then that's what you find. On the left, you have the distances between subjects. Subject 1, subject 2, and so on in different sessions for the functional connectivity and for the scaffolds, okay? So functional connectivity works already. You already see a little bit of a block structure there. So it means that you're actually more similar to yourself than to the others. But the scaffold is like much, much better. It's actually, if you do this for the whole 100, it's like pretty much ridiculous, okay? The way it works. You can quantify this effect, for example, by looking at the effect size. You can look at the distances intra-subject, so myself with myself and myself versus the other person. And then if you look at, for example, you can do this in many ways. The effect size is one. Functional connectivity is already giving you a very good effect size. So you can do fingerprinting with FC. It's not that you don't, but it's ridiculously much larger for a scaffold, okay? It was so big, and actually the result was actually true, and so held up for all the, for a bunch of different window sizes, and we tried moving around the window, so it seems to be there. It was so powerful that I actually thought that the student leading this must have done something wrong, right? Because it's too good to be true, come on. I mean, these scaffolds are actually very sparse, about 2%, 3% of density. So we did it again with a different atlas, different subjects, and the results are the same. If you play around with different parcellations, the numbers change a little bit, so it can get better. For example, this was with the Yale. We did it with the AL, and the results are not so good, but they're still good. So qualitatively, we get the same thing out, okay? So scaffolds are fingerprinting people very well. Yes?
Just wondering if
Sure.
one wanted to try and build a classifier for the image.
It works.
Would you do the scaffolds do roughly as well, better, much worse?
Much better. We did this with all the possible ways you can do it, and the scaffold does. So the FC already does well, like around 90. I don't remember the number. I think it was 89 or 90, and then the scaffold was like 97, 98, something like that.
So somehow magically this manages to capture exactly the features that are also.
I am as surprised as you are right now, but I tried to do everything to disprove myself, and so far it seems to be working. Something that is interesting, though, is that, sorry.
I just have a quick question. Did you try any atlases that you can do as a functional scale, like Lausanne or something, to try to
No,
look
we
at
didn't,
resolution?
because it's a lot of time series of windows, it's a lot of subjects, and it's long. So, but yeah, of course, we should try. We haven't done it yet. This is actually impressive exactly because we've been doing a bunch
So
of
these are
trials.
about 100.
It's 100 subjects, but then you have all the windows
No,
for all the width. Here it's 400,
It's how many?
300 something.
You're in the 300.
Yeah.
Okay. I'm just curious what resolution you're at.
It's yeah. I mean, I don't remember. I'm not gonna commit to which atlas corresponds to this picture. I'm gonna commit to the interpretation of it. So trust me, we can pick up the notebooks later. Yeah.
Now, does it matter that you're doing this on a correlation matrix versus, say, a precision matrix, which, frequently when people are thinking about sparse representations of interactions between variables and stats, they look at the precision matrix.
Yes.
Consider that sparse when the correlation matrix might be super dense.
So the reason why we use correlation in matrix in this case is because in natural neuroscience, that's sort of the holy grail. And that's what not holy grail, actually. It's the common standard. That's what everybody uses in this case. Scratch the holy grail at all. So that's what we did. I'm going to show you in a second something else where we didn't use correlation matrices, okay? So you're going to probably like it better. Still fully connected, but it's way simpler complex. What I wanted to say is that then you can ask, well, where does this power come from, right? So is it always this? So I've done this at the whole brain level. What if I look at some functional subnetworks, right? For example, if I look at a typical functional subnetwork, frontoparietal, blah, 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 results are still good. If you check here, the effect sizes, they're smaller, okay? Compared to the whole brain thing, the whole brain level, okay? So if you look inside functional subnetworks, you don't do as well. Something that I wanted to show you, but exactly as I said, I could not find the picture, the right picture, is that if you then compare these with the functional connectivity inside the subnetworks does better, slightly better than this, okay? So the global level, if you take the whole brain, the way we compute the scaffold, this is much better, though if you look inside, it's not, with respect to the functional connectivity, although it's still good, right? Yes?
Is it because there's not enough data points?
There are two possible explanations which we are looking at, and one is the density, so you don't just have enough stuff there to see the difference. That's part of the answer. I think the other part, more important part, is that these cycles that we're building typically can cross through a bunch of these different subnetworks. And also, if you think about how this is built from the correlation matrix, basically the groups of nodes that are strongly connected, they're like 1 point. And then you're going to find cycles not inside there, long-living cycle, but long-living cycle between these things. So it's like, my interpretation, the way I'm imagining this, is that we are basically extracting like a watermark of the functional connectivity structure somehow, okay? This is the idea. Good, it works. We have this capital capacity, no idea on the origin, so we don't really know where this comes from. Actually, quasi-idea, which is like alpha interpretation, but non-interpretation, alpha link. Let me show you what I mean by that. So we tried to go back to the information theory that I just mentioned earlier, and in multivariate information theory, higher order information theory, there are basically two notions of how nodes or multiple nodes can share or have synergistic information. You can have two nodes that have a lot of redundant information. You can have three nodes that are like synergistic. So you can only see some properties of the system when you look at the three of them together. Now, our problem, and that on the left is recent results on the redundant, the red, and synergistic structure of fMRI data in people addressed to from wireless ports and so on. Our problem is that here we have the scaffolds, right? The scaffold has edges the way we built it. So we need something that is defined on the edges. And so we actually went back to something else, which is a proposal by Lupi, Rosas, and collaborators a couple of years ago, in which you're basically looking at how much information there is in a pair of nodes, so an edge, right, with respect to their future. Okay, so how well they predict their future in terms of the redundant information between the two nodes and the synergistic information. So can you do better if you actually look at them together, or if it's just extra information? Okay. So we did this again, blah, 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 in our data, blah, blah, blah. We do it again, and then the first thing you of course want to do is see whether there is some correlation between the edges that you find in the scaffold and the correlation matrix already. And we find that of course the edges in the scaffold tend to have a larger than random, if you pick a random in the matrix, correlation value in the original matrix. But that's obvious by construction, right? Because we start from strong correlations and we go down. The interesting bit is that when we look at the amounts of redundancy and synergy, here are the values, distribution of values for the edges in the scaffold. And over here instead are the values if you just pick from any other edge in the, in the matrices that you have, okay? Now, so we see that the scaffolds are a bit more redundant, and there's also a significant effect here, it's small, and it's a bit more synergistic than the ones at random. Now, what is interesting here is that they are by far not even near to the maximum redundancy values and maximum synergy values, okay? So in this sense, even if there is like a bit of a structure there, what we're seeing is that the scaffold edges, they're boring edges. They're like in the intermediate range of information content, of synergy content, or redundancy content, and so on. And I don't really know what is the interpretation for that. I have an idea, but I don't really know how it goes. So summing up this first part, and I'll take 2 questions, otherwise I'm never going to finish this thing. So we have this like very strong topological information that is able to discriminate among individuals. These mesoscale markers, in the sense that I described earlier, so the cycles and so on, they're very powerful. They seem to be related somehow to the local higher-order information properties, but they don't seem to be sufficient. They don't give us like, oh yeah, of course, the scaffold is getting all the synergistic edges and so on. Yeah, so we don't really know where that comes from. There is a further limit of this, which, even though I played with a lot of different window sizes in my slicing, still I was doing this with the median was about 100 TRs and so on. Okay, so this is still pretty long, 300 seconds roughly, 250. So if you think about that. Before I continue, any other question here? Now, yes. You don't give them too much, actually, and you ask them. So they need to be expert, but not too expert. Otherwise, they know that they're not high very much. So when you give the placebo, for example, the same experience were not possible with ayahuasca, because people that that are used to ayahuasca realize that either that you've given it to them, because if they're not used, they just puke all over the place, and the ones that are not gonna puke in the scanner, they are basically Santo Daime followers, and so they know the feeling, and so head motion was a problem, but as you can imagine. Yes.
So you might have said this. Did you have any structural MRI on these to try to ask
when we did are you talking about this one or the latest one, the fingerprinting one?
Yeah, to see if if it's something that is picking up about a structural thing, maybe that the functional is...
We have it. We have not looked at that, but the result that I showed you about the redundancy sort of really semi-disproves that, because we know that the edges corresponding to the strongest fiber, at least in DTI, for example, they tend to be very high redundant. So no, we have not done the check yet. It's part of
I just know that like structural, you're much better with structural than functional.
Yes. The problem there is that I cannot really build net easily a space. I can do embedding, so I need to do a little bit more games. Instead, here I just have like a correlation space I can use. Okay. Can we go lower in time resolution? And the answer is yes, although we need to do something very a little bit dirty, and let me explain why dirty. And well, I'm just going to tell you, and this is the paper that came out last year that does this. So taking inspiration from work by Betzel, Spors, and so on, we created auxiliary time series for edges, triangles, tetrahedra, everything else. How did we do this? We basically took the time series for the nodes, and in the case of edges, we basically multiplied them entry-wise to each other with an appropriate normalization. What is the meaning? Is that the idea is that this conveys a notion of co-fluctuation up or down of the edge, right? Same thing you can do for 3 nodes, 4 nodes, and so on. There is a problem, of course, that if you suppose that you have 2 fluctuations down, 1 up in a triangle, it's going to give you plus, right? But we would like to have all 3 ups or all 3 downs, okay? So we put like a parity in there, and so if they're all coherent, all up or all down, then we put a plus sign, otherwise it's a minus sign, okay? And informally we call it Nazi coherence for us, right? And so basically what happens is that you have for every node, every edge, every triangle, blah, 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 a time series. So at every time point, you have a weight for every simplex, okay? So lo and behold, again, you have a weighted simplicial complex. Now there is a problem though, because the weights, if you want to filter it, so you put the nodes in, then you start putting in edges, triangles, whatever you have, depending on the weight of this co-fluctuation measure that we just built. Problem is that the triangles could come in before the edges, and that's a problem for a simple feature complex, okay? So, or the tetraeder and so on. In this case, we only did low dimension, so edges and triangles. So what we do here is whenever we find a triangle that comes in before its edges, we just take it out, we put it aside, we call it a violating triangle, and in this way we create a cleansed, a purified filtration, and so you can do persistent homology over here, okay? So we have the list of violated triangles with their weights and the persistence diagram. For how we built the science with this parity measure, you start from coherent fluctuations, everything up or everything down together, and the negative are the ones that are incoherent. So in the persistent diagram, you have three regions where you start from coherent generators that basically starting positive weights and dying positive weights, positive, negative, 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 coherent, 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 and so on. So on top of the persistent diagram, you basically have some subsectors, and for example, you can count how much persistence you have in each of these, and you can make like another little last triangle, two many triangles. This is a plot that shows how close you are to any of these. Okay. So summarizing, time series, weighted simple complex, and we extract hypercoherence, which is this number of violating triangles, and then what we call hypercomplexity and the scaffold. Okay. Now, what does it do in a system that we know? So for example, if we take a chaotic map, a dynamic map, where we can control the dynamical regime in which we are. For example, we can be in chaos, pattern selection, so on. You can see that already like hypercoherence, total persistent complexity, and so on, they pick up differences between these regimes. Okay? So at least there is hope that in a case where we control, this is gonna actually show differences. And the same thing if you look at the triangles and the scaffolds, but we don't really need it now. In that paper, the one that I just flashed to you, we looked at this, looked at a bunch of different data sets coming from, for example, epidemic, financial data, brain data, and so on. And you see that there is a little bit of variability. But the important thing is that basically, in every case, the colored parts are different from the gray curves, and the gray curves are a null model in which we randomize the time, keeping some constraint on the structure of the whole thing. Okay. Now. Yeah, no, I don't think I'm going to do this. I want to just show you something that is cute, but I'm not going to do it. I'm going to show you later because I'm able to predict diseases using this thing, but just ask me later. So, predict diseases, what type of disease are we looking at? So what do we do with this? We go back and we take again a bunch of data set, 100 subjects again, two different groups of people, just people like 100 as a number. And we also have a bunch of cognitive tasks in this data, so not just resting. We repeat the pipeline that I just described. We create the time series, blah, 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 and we do the whole filtration. And we end up with something that looks like this. We have the hypercoherence distributions per task, those little persistent triangles, whatever you want to call it, per different tasks, and they all seem the same. Which is bad, right? Because it means that these global topological indicators, they don't really discriminate between the different tasks, okay? So again, we need to find a way of localizing this topology, or at least looking at where this thing goes, and see whether we can actually pick up any difference. So how do we do this? Well, and also we'd like to compare these to other representations. For example, what if we do this comparison at the node level using the FC, at the edge level using the edge time series that were, the fluctuations and so on, okay? And the way you can do this is, well, in the case of FC, for example, you start from the bold matrices, you can look at the correlation that they have over time, and then you average over subjects. And the idea is that if you have the same ordering of, say, rest, task 1, task 2, task 1 again, task 2, and so on, the similarity of the matrix should be, the more similar, the better that measure, bold or triangles and so on, captures that task structure, the more block diagonal this matrix should be, and the fuller these things are. Right? So we do it, and you end up with something that looks like this. Okay. So again, you see that going from left, which is low order, bold at the level of the nodes, to higher order, the scaffold, the blockiness increases. Okay. So again, scaffolds seem to be good at. And also the triangle structure. So here we are taking the list of violating triangles and we're projecting like a mask on the brain and using that as a vector. It goes better. And this value here is element-centric similarities, just to say how similar they are in here. Okay. Now, this is beautiful. So maybe we can do fingerprinting also in this case at the single TR level, a single resolution. So we do the same thing that we did before. So you have the 2 sessions, you test, and then you do the retest. In this case, we're using a different measure. I apologize, but this is because it's a different group of people that I've done this with. And the idea is that you're measuring something that's called IDIF. It was created by Hawking Gonya, I think. And the idea is that suppose that you have your subject, test and retest. You would like to be as close as possible to yourself. So you would like the diagonal blocks to be stronger. You would like the rows to be low, which is what you write here. And then they invented this measure, which is actually pretty bad, but it works. And it's the difference between how similar you are to yourself and versus how similar you are to others. We do this, and we find very bad results. Okay, so if we do this at the global level, the whole brain level, we find basically that we cannot really fingerprint. What we can do, though.
Sorry.
Yes.
You cannot really fingerprint, but you can tell whether the subjects are doing memory tasks versus you can.
Yes.
Okay.
Sorry. Yes. That's the blocky thing before. I can, in a sense that you can already with FC, but you do it better with using these violating triangles or the scaffold. Okay. So this information. If we try to do fingerprinting, it's really, really bad. Actually, surprisingly bad at the single time level. But if we start looking at the at the subnetwork level, visual, somatomotor. I'm going to be done before that, I think. Somatomotor and so on. And then I try and I measure this IDIF for, bold, for edge functional connectivity, so, the edge by edge matrices, and for the violating triangles. You see that basically in all cases, the violating triangles do better, okay? Or equivalent to the others, okay? Violating triangle, let me remind you, are the ones that confluctuate more than their edges, okay? And that we took out to be able to do persistent homology on the remainder. There is a glaring absence there, right? There are no scaffolds. Why? Because scaffolds are basically down here. They're really, really bad at doing this. Also in the case of, when you do this by block, just like before, okay? You can actually remap your triangles on, on the various subnetworks and see, for example, the variability between subjects and so on, okay? What do I mean by all of this? Well, let's sum up what happened here. So we have this evidence that global higher order indicators, they're not really able to distinguish between subjects in this way at the very short time scales. We have that this local higher order information is able to distinguish tasks within the same subject. And we also found that these localized hypercoherent triangles, they seem to be the best we have, among all these things. Now, the conundrum here is that we find that at the global level, the scaffold, the whole global, the whole brain level, the scaffolds are very good at the long time scales to fingerprint. At the short time scales, instead, the scaffolds are really, really bad. And instead, these localized triangles, they are very, local structure because it's just the triangles. If you look at them, they're very, very good. Okay. I don't know why this is happening. Our guess and hope is that what's happening is that you have at short time scale, so instantaneously, you have this coordination, local coordination in triangles that basically echoes, resonates through scales, and then it becomes very important at the level when you have longer time scales, okay? I don't have evidence for these. We are actually trying to explore these using computational models, virtual brain, or at least, dynamic mean field models and stuff. There is some evidence that it's probably true. Of course, you would imagine, right? Because the scaffolds that I showed you at the beginning, they coordinate basically very large, modules that are disconnected between each other, at least that are not, locally segregated, typically, okay? But we don't really know. So this is actually next work. That said, let me finish. Those are the people that have been involved in various combinations of the things that I mentioned to you. If you're interested in this work, or at least in general, in this sort of higher order interaction, there is a perspective out, and there is actually a book with a bunch of people that contributed to it. So please go there and look at it. Couple of announcements. We are hiring PhD students in Northeastern London, so send us your best. And we're going to be hiring even more in Europe, actually, not UK, because there is a Marie Curie doctoral network that just got funded, and this is gonna be 10 positions between a bunch of places all across Europe. So again, send us you're even better than the ones before, because these guys are going to be paid, or well, these people are going to be paid very well, and they're going to have a lot of money to travel between the different groups. With that, the faces of the collaborators again, the slides are there, and I'm very happy to take any question.